All right, so the first thing I learned when I got to hydrogeology class was that there are no such thing as underground rivers. You know, a point that continues to get beaten into my head, even though I refuse any longer to accept it. These are the things, the tenets. Groundwater flows through the spaces between the rock grains, and if you take a look at the diagrams, I'm trying to illustrate that. I learned that groundwater flow is a diffuse and slow process. I learned that velocities tend to be on the order of feet per year, or sometimes even less. And I learned that the mathematical concepts that we were taught, they evolved out of a sandstone aquifer, the great sandstone aquifer of the Midwest, the Ogallala aquifer. And that by mastering these concepts, it renders the aquifer storage and contaminant movement and groundwater movement to be very predictable phenomena. And the other thing I was told is that amateurs study springs and professionals study wells. Okay, so these are the things that I learned in my first class. They didn't sit really well with me, given that 4 days a week I was diving in these caves and feeling flow blowing so fast that if I stopped kicking it would shoot me out the other end at a rate quite a bit faster than feet per year, I can assure you. But some other things that I learned that did really resonate is that water flows down gradient. It always flows down gradient, no matter where you are, no matter what rock you're in. Inflows always equal outflows. But then in terms of the hydrologic cycle, this is sort of the concept that we're taught, is that you have rain that infiltrates the ground, and the infiltration accumulates in the aquifer, and then the water flows through this diffuse process on its path to rivers and streams and ultimately the ocean. And that the aquifer itself, even though groundwater flows very slowly, can have an enormous amount of storage. Okay, so the next slide. This, however, is a little bit more close to how I saw it, which is pretty much the same thing. Water still flows down gradient, even in karst. Always flows down gradient. Inflows still equal outflows. But groundwater is a fast convergent flow process. And two important things to realize here is that the difference between these two models, and that's what all of this really boils down to, is a model of how we think the world works, is that in the karst system, groundwater flows really fast, and there's a lot less storage. So there's a lot less water in the aquifer, and it moves through the aquifer a hell of a lot faster. Excuse my language. Okay, so here's what the difference is between these two models. Now here what I'm doing is I'm simulating a river. You know, this line represents a river, and there's two springs on the river. In the diffuse flow model, basically what it says is groundwater flows diffusely, meaning evenly and slowly through the aquifer, and it converges onto the river, and that the river gains. Here I've got my measuring stations. It's 100 CFS upstream and 200 CFS downstream. So it picks up 100 CFS. It's a gaining stream from the groundwater discharge. And that gain is occurring all along evenly across the reach of the river. Of course, if you spend any time on Florida rivers, you realize that that's not really what it looks like, right? You paddle along the river, and then you see a spring. And so it might gain exactly that 100 CFS, but instead of it gaining it evenly across the reach of the river, it gains it at, in this case, 2 discrete points at the 2 springs. And you can see the pickup, you know, with your own eyes as you paddle down the river. And the difference here is that this one, there must be convergent flow in order for this to be true. There must be conduits that connect to those springs. And those conduits must collect water from an upland recharge area and then convey it to the springs. So that's the difference. And this is what it would look like if I rendered this in 3 dimensions. This is just a hypothetical image here. We have a conduit. This block represents the water table, or the potentiometric surface. It represents the aquifer, the part of the aquifer that's got water in it. And what the conduits do is they create troughs, like canyons. How many people have ever, you know, hiked through a canyon? All the water drains into the canyon, and then the canyon picks up the water and delivers it out the other end. And that's exactly what's happening in the aquifer because of these conduits. Okay, so next slide. So this is kind of what the models break out. You know, we kind of get a little more technical, but now, really, as a scientist or as an engineer, our challenge is to take these models of the world and then do something useful with them, right? To be able to make predictions or to help guide people in their decision-making processes. Well, we use math to do that. And as it turns out, it's a hell of a lot easier to write and solve the equations for this model of the world than it is for either this model or that model of the world. Now, you ever hear the joke about losing your glasses and the man's looking on the ground for his glasses and the other person comes up and says, "You lost your glasses, where'd you lose them?" "Oh, I lost them in the other room." I'm like, "Well, why are you looking in this room?" "Because it's light in this room, it's dark in the other room, I can't see." I'm like, well, that's kind of where we're at. Basically, in the early 1970s, as we started to evolve in the 30s, 40s, 50s, 60s, all the way into the 70s, as we started to evolve our knowledge of groundwater flow systems, both karst and porous media, the limitations on our ability to compute the mathematics behind them drove us to this model out of necessity. But for the last 20 years, we have not been here as a form of necessity. We can quite readily, and there is software available right off the shelf to help us deal with either this model or with the model of conduits. But what I'm going to talk about is the consequence of us being firmly rooted in the estimation or the assumption that the Floridan aquifer is this porous media, this sand model. Next. So this is what the Floridan aquifer looks like. And to the point that was brought up earlier, there is differences in the aquifer. This map shows the confinement in the Floridan aquifer. This region in the lightest area we call the karst belt. It's where the aquifer is unconfined. So basically it means that there's literally nothing of substance that impedes recharge from occurring directly to the Floridan aquifer anywhere where this light area is occurring. And all these black dots are first magnitude springs, meaning that they discharge more than 100 CFS. And all these white dots are second magnitude springs, second mag springs, which means they discharge somewhere between 10 and 100 CFS. And you can see that the concentration of these is pretty highly favored into the unconfined region, but it's not all in the unconfined region. All of these springs are discharges from the Floridan. The darker areas are where the Floridan becomes progressively covered by thicker and thicker amounts of confining material. And what that confining material does is it impedes recharge. So you can pretty easily look on a map and you can think about where you are today. The fact that there are all these streams and lakes and everything else in the Orlando region is only because you're on the confined material. Because the water, it doesn't recharge rapidly through that material and get into the Floridan aquifer. Okay, so that's what the confinement does. So there's three areas that I'm going to kind of refer to today. Actually, 4 areas, but most of the time I'm going to talk about the Wekiva Springs area, which is up here in the Big Bend, south of Tallahassee. I've been studying the Wekiva area for probably 13 years with the Florida Geological Survey. We chose Wekiva for a specific reason. The idea is that, you know what, the idea of, the great thing about science is that you hold one or a couple things true, is that if you can understand processes, then those processes become more broadly applicable to other regions, right? So instead of studying individual things all over the state, we decided to focus intently on one area and study it to death so that we could identify how it works, identify methodologies that are useful for the characterization of that type of hydrogeologic environment, the karst hydrogeologic environment in Florida. So that's why we studied in Wekiva. I'm going to talk a little bit about this area on the Santa Fe and Swanee River. This is the Silver Springs area. I got a slide on that. And then, of course, this is where we are over here on this marginally confined part of the aquifer. Right in what we're talking about is a collection of second magnitude springs that discharge out to the Wekiva River. Next. Okay, so this is Wekiva. This is it's a big spring, 120 to 1500 CFS, depending on what day you measure it. So that's somewhere between on average 250 million gallons a day, and it peaks out at over 1 billion gallons of water per day. Creates the headwaters of the Wekiva River. Glass bottom boat tours probably won't be able to ride those very much longer because the clarity of the spring is disappearing. But if you haven't been to Wekiva, I highly recommend a vacation to go up to Wekiva Springs. Yeah?
Sorry, the acronym again, CFS stands for?
Cubic feet per second. So yeah, not a problem. So it's about I don't know, about how many heads per second. All right, next. All right, so can you move your mouse and click on this part of the black? Click. And click on that part on the other corner. Awesome. Thanks, Bob. All right, I thought I'd let you, it's only going to show one at a time. Well, let's look at one at a time. I thought I'd just let you see a little bit about what these caves look like. These are caves from the Wekiva cave system, as I was saying. This is actually, I stole this from a video that was made by for Japanese public television. But this is the part that's really cool. How many people have seen it, The Abyss? Anybody ever see the movie Abyss? Well, they use the same technology to show you what the caves look like. Oh, sorry. Click on the other one really quick. This is a good one. We got enough of that one. Oh, okay. Keep clicking on it. Why is it stopping?
What's that fall?
Those are divers. Yep, so now they're entering into the cave system, and this will give you a little sense of what the caves look like. Now, Wekiva, I'm not here to tell you that Wekiva is like Wekiva. Remember I told you at the beginning I was barely able to squeeze through the passages of Wekiva. Wekiva is the longest underwater cave in North America, and it is some of the largest cave passages, underwater cave passages that have been observed anywhere in the world. But what I will tell you is that the processes are the same in terms of the capacity of those conduits to transmit water relative to the capacity of the rock around it to transmit flow. And go back to a little story. When I was an undergraduate, I of course was diving every day, and they were teaching us that there's no such thing as underground rivers. And we had my professor Dan Spangler invited Wes Skiles to come to our classroom, and I didn't admit to many of people at University of Florida that I was a cave diver, so I kind of tried to keep that under wraps. But when Wes came, he showed videos of the caves that I was diving in, and everybody was really impressed and blown away. And Dr. Spangler appropriately pointed out that karst was described in our textbook. It accounted for the one paragraph of the one chapter in our textbook that said basically that everything else in this textbook is not relevant to karst environments. Okay, so that was the one paragraph on karst. A little while after that, one of the professionals from Swanee River Water Management District also came to our class, and though I regret to say I didn't have the courage to challenge people on the differences between what we were being taught and what I was seeing in the caves, one of my classmates did. And they asked the professional, "What's going on?" You know, basically he came and he was telling us about how all of these methodologies, you know, for characterization of the aquifer are duly applied in the management of groundwater resources. And one of the questions was, well, how are these methodologies, you know, how do you deal with karst in the presence of caves in the Swanee River Basin? And he said, well, caves really don't exist. And so the student said, well, we just saw the video from Wes Skiles. And he said, Wes Skiles fabricated all of that stuff. because he's a Hollywood guy. They really don't exist, or if they do exist, they're just anomalies that are irrelevant. So in other words, you don't have to worry about them. Just continue to focus on the porous media theory that you're being taught, and everything will be fine. So that's kind of where we're and to me, I think that's largely why we are where we are today. So this is now Wekiva, unfortunately. It's pretty overgrown with algae and a massive hydrilla problem. Next slide. As you know, Bob showed you, you know, he took care of the whole state here, but this is you know, ad nauseum. Any spring you go to, you see that you have early levels where nitrates are really low, and then as you move into the more recent decades, nitrates are up. You know, in this case at Wekiva, They peaked out at above 1 and started to stabilize somewhere between 0.8 and 1 milligram per liter. You know, lots of studies identifying sources. Sources were septic systems, wastewater treatment, fertilizers. Sounds familiar, right? So industry. Move on to the next level. So the question was, you know, well, what is the hydrogeology and you know, what do we know about the system so that we can identify, we can narrow down those sources, and we can identify the bad guy so that we can, you know, make the bad guy pay, so to speak. And that's, you know, sort of to be the recurring theme. So here's what was known about the Woodville Karst Plain where the Wekiva sits in and around 1990. So basically, the why I've dated it is because these blue lines here were the mapped caves that had been mapped by the Woodville Karst Plain project divers. So this is the Leon Sinks cave system. This is Chip's Hole. This is Indian Springs, and this is the small Wekiva cave system as it was mapped in and about 1990. All these brown lines are rivers that disappear at places that we call swalettes, where they go completely underground. And so you have Lost Creek, Jump Creek, Black Creek, Fisher Creek. This is the Munson Slough that takes about 60% of the city of Tallahassee's stormwater, comes through Lake Munson, and then ultimately goes underground here at these swalettes called Ames Sink. And over here, I don't have the center pivots on them, but this is where the city of Tallahassee spray field is located. So what do we know? We know from wells that water always flows down gradient, and flow is converging from the north, from the west, from the east, and it's flowing into this big trough here that is called the Woodville Karst Plain. This is where all of these springs are located, and then ultimately flows out the Wekiva River to the Gulf of Mexico. Wekiva Springs, the third largest spring in the state, like I said, average discharge about 250 million gallons a day. Spring Creek, formerly listed in the books as the largest spring in Florida, probably a comparable discharge, but people estimated that it might be twice or 3 times more flow as Wekiva. And then St. Mark's River Rise, again, a comparable discharge to Wekiva in terms of magnitude. So you have these 3 major spring discharges that are just emitting rivers of water into the Gulf. And then, of course, all these other stars are second magnitude springs, some comparable to Wekiva, most of them quite a bit smaller. So what we also knew is that we had done age dating studies that had labeled the Wekiva Springs water at being 40 years old. Right there, that was a key point of scientific data. Sprayfield went in about 1980. And this was about 2000 when we were having this discussion. The water at Wekiva Springs is 40 years old. So what's the conclusion? If the water's 40 years old, how can the nitrate at Wekiva possibly be coming from the spray field? Because the nitrate at Wekiva must ergo too be at least 40 years old, right? So we have these age dates. We also have groundwater models that suggest that flow is around 0.1 to at most 25 feet per day. So again, you look at it, this distance is 12 miles, 0.1 feet per day. Gives you an idea that the spray field is a really long way away. It's not a high source of water. Now, note one thing. These lines are what we call the potentiometric surface, and they essentially, the lines on the outside are the high lines. So this is the canyon that I showed you in that earlier image, okay? And this is the flanks of the canyon. All the water is flowing in. If you look at the potentiometric surface, the spray field is here. The gradient is here. So there is a pathway, and that was duly noted by the Northwest Florida Water Management District. But nonetheless, what people keyed into was the 40-year age, the travel times, and the relative proximity of Wekiva to the spray field versus St. Mark's to the spray field. And so the dominant thinking at the time was that the nitrate at the spray field was going to St. Mark's, not to Wekiva, okay? So next slide. So now what I'm going to do is I'm going to take you through a series of scientific investigations that we did, groundwater tracing experiments that we did in the basin to try to better understand the flow paths to Wekiva Springs, to maybe learn more than what we could learn simply from the age dates and the potentiometric surface maps. So we engaged in this, remember I'm the guy that kept diving after I got pinned, right? So I'm not the smart, brightest bulb in the box. That's why I like to key into things like groundwater tracing. It's pretty idiot proof. You put something in the water and then you go, and if you find it someplace else, whoo, I've got a connection. And I can measure the distance. Well, when we first came in, when I first showed up in 2000 and I got together with Rodney DeHaan at Florida Geological Survey and we talked about what we wanted to do, the powers that be didn't want to hear anything about tracing work. We didn't want to hear anything about tracing to Wekiva Springs because it was believed it would be impossible because Wekiva was too big of a flow. In other words, if you put some dye in the ground, it's going to be so diluted with the flow at Wekiva Springs that you're never going to see it. By the way, a dye tracer test had been done maybe 20 years ago where they put some dye in at Ames Sink, the sink that takes the discharge water from the city of Tallahassee, and they didn't see it at any of the wells that they tested around there. I wanted to point out that they didn't bother to look at Wekiva Springs, but nonetheless, nobody looked, so they didn't find, the tracer test didn't work. Anyway, we know that, we also know that, of course, there are no such thing as underground rivers, and nobody was paying attention to this suspicious thing that looks like an underground river. So we wanted to go in and do some tracing. So the very first trace that we did, I proposed, well, we're going to put some dye into one sinkhole, and we're going to measure it at another one. And I was pretty sure it would get there because I'd already swam that distance, okay? So I loaded that shotgun to make sure that I would win a successful trace. So go ahead and click through this, Bob. So that was it, and it was Sullivan Sink to Sherrill Sink, 1.6 miles, traveled 8,800 feet per day. And I said, oh, wow, look, we're successful there. We might as well go over here to Fisher Creek, and maybe we can see where it goes. And lo and behold, Fisher Creek 2 travels at about 3,700 feet per day. We did it at Black Creek. And this time, same thing, about 2,600 feet per day. And this one was interesting. Don't go any further than that. But at Black Creek, I kind of, again, loaded the shotgun. We put some extra sampling stations further down in the cave system. And we saw, hey, this little bit of dye that we put at Black Creek keeps on going, and it heads suspiciously toward Wekiva Springs. And we could track it all along its path. The other thing that we learned is at the same time we were doing a collaborative study with some age daters, and I asked them to age date Sherrill Sink, and the age date came back at 35 years. So not wanting to be too much of a smart ass, I said, okay, well, if the travel time is what we get from the tracer test, and presuming that this is a continuous process, with a porous media aquifer, then this water must be coming from 21,000 miles away. Because you told me how old it is, and I'm telling you how fast it's going, and the only way to rectify those two is to tell you that it came from right about here, but instead of coming here directly, it went around the world. So with that one, I was actually able to get some more funding to do yet another trace. And we went ahead, we step out a little bit further. These are the traces I just told you about. By 2005, the divers, my buddies in the Woodville Karst Plain Project had done a lot more diving, a bunch more exploration in Indian, really explored a lot of cave in Wekiva. So now it's, if you look, Wekiva is getting close to being about the same size cave system as Leon Sinks. This is 11 miles, so you're talking about many miles of mapped cave passage by this time. Okay, so now go ahead and do this. We're going to do some more tracing. We injected at the same point in the cave system where we got the detection from Black Creek and Fisher Creek, and we tracked it all the way through this cave through many sinkholes. We had drilled a well into Wekiva, and we saw it come out at Wekiva, and then eventually, so we know it came into the cave system down here and then turned and flowed north back up to the spring. The bottom line is it traveled 10.3 miles, 7 days. The velocity there is over 1.5 miles per day. So with this one in mind, they asked us finally to say, okay, why don't you guys trace aim sink? This is 60% of the city of Tallahassee stormwater runoff. Let's go ahead and trace it. We did one of the sinkholes, Kelly Sink, traveled to Indian Springs, 5.2 miles, 13 days, about 2,000 feet per day. The next one we did from aim sink itself to Indian Spring as well, 5.2 miles, 17 days, 1,600 feet per day. So we went ahead and did a trace from Indian, saw that it connected into the Leon Sinks cave system and then flowed down, makes the loop to Wekiva, and we get 5.5 miles, 5.9 days, about 5,000 feet per day. So the bottom line is whatever goes into aim sink is going to show up at Wekiva Springs approximately 2 weeks later. That's the takeaway message. So whatever is on Tallahassee streets, you're swimming in at Wekiva 2 weeks after that. Okay? So next slide. So the big question then became pretty quickly, wow, if you guys can do all this with dye tracing, what about the spray field? Well, what's in between here? There are no conduits. The spray field is up on the margin of the confining unit. Depending on where you are in the spray field, you're literally on the toe of the clay. So in some places there's confinement, other places there isn't. Spray field was chosen, of course, for high infiltration rates, so it's real close to that edge. But there are no mapped conduits. No matter how many holes my friends climbed into, sinkholes out here, they couldn't find any caves going towards the spray field. So it was a big difference, instead of tracing through known caves or from known swalettes, we're going to be tracing from the spray field. But here, the purpose is, of course, to say, does it go to Wekiva? Does it go to St. Mark's? Next. This is what the spray field looks like. Two things to point out. These are the ones that we talk about because we're hydrogeologists. There's all this water flowing onto the ground and it's infiltrating quickly. These plants aren't taking it up fast enough. Of course, they actually found out at the spray field that they had to add fertilizer in order to grow anything because the infiltration rate was just too high. So they added fertilizer, they added cows to try to make this an economically viable farm, basically, was what their goal was. So the other thing, though, to note is that there's all these cows wandering around the field. I'm the hydrogeologist. I didn't pay attention to the living things. Next. And I'll tell you why that becomes relevant soon. But this is what dye tracing looks like. Basically, you get a whole bunch of, I call it the witch's brew. If you put your hand in this, it will turn color. So you can trust me, or one day you can test it. I, of course, had to test it. Yeah.
That last slide, spray field water from fertilizer runoff, or was that because?
This is the city's treated wastewater effluent. So it goes through secondary treatment, and so now it is technically drinkable water, I think.
About 8 to 10 milligrams per liter at that point.
And it's about 8 to 10 milligrams per liter nitrate at this point.
It's due to